In our channel's videos, we often talk about quantum mechanics, and almost always, we end up discussing the so-called Heisenberg uncertainty principle. This isn't surprising, as the uncertainty principle is the foundation of quantum mechanics, from which the vast majority of its strange phenomena stem. Virtual particles, the tunneling effect, quantum entanglement, and even the fact that electrons in an atom don't fall into its nucleus despite the electrostatic attraction. All of this is ultimately explained by the uncertainty principle. To even begin to understand quantum mechanics, one must first grasp the uncertainty principle, which, as practice shows, is often misunderstood even by those interested in physics. Let's start with the formulation. The uncertainty principle states that certain parameters of quantum systems cannot be simultaneously determined with absolute precision. The most commonly discussed pair of characteristics of a quantum object is its position in space and momentum. Specifically, the object's coordinate along a particular axis and the momentum projection on that coordinate. We say that the product of the uncertainties in determining the momentum and the coordinate cannot be less than half of Dirac's constant, i.e., Planck's constant divided by 4 pi. Sometimes you might see this written without the half, which applies when we're talking about the uncertainty in measuring changes in momentum and position, which happens quite often. However, the canonical and strict formulation includes the factor of 2 in the denominator. Position and momentum projection are the most well-known quantities related by the uncertainty relation, but they're not the only ones. For example, the same relation applies to energy and the time interval. We cannot precisely determine the time in which a system will be in a state with an exactly defined energy. There are other examples of parameters connected by the uncertainty relation, such as current and voltage, or the intensities of electric and magnetic fields, among others. But today, we'll explore the essence of the uncertainty principle using the classic position-momentum pair. What does the uncertainty relation mean? The more precisely you determine the position of a quantum object, such as a particle like an electron, the less accurately you can determine its momentum. In other words, if you determine the momentum with absolute precision, you'll lose any ability to say where the particle is located. Conversely, if you pinpoint the position exactly, you'll lose all certainty about its momentum, meaning you won't be able to say anything about where or how it's moving. In every specific measurement, we always obtain a definite value for both position and momentum, as well as any other parameter, but we can never predict exactly what these values will be, and each time we measure, we get different results. The problem with the uncertainty relation is that this formulation of one of the strangest concepts in quantum mechanics doesn't sound all that unusual. Even in basic school physics classes, we're told that we can't determine the exact values of certain physical quantities in an experiment. Yes, we can measure them and obtain specific values, but our measurements will be accompanied by errors due to the imperfections of our measuring instruments. And even when measuring the same characteristic of the same object, we'll get slightly different values each time, as the instrument's inaccuracy may vary. It might seem that the uncertainty principle is something similar, or at least in the same category. Sometimes, even in fairly serious literature, you'll find explanations of the uncertainty principle as a measurement problem. The idea is that to measure a parameter of an object, we must interact with it somehow, and this interaction changes the object's parameters, leaving us unable to know what they were before the measurement. Here's a classic illustration used in this context. Suppose we need to determine the position of a moving quantum particle, such as an electron, at a given moment. To do this, we might bombard the particle with other particles, such as photons. Some of these photons will collide with the particle and change their direction. By determining which photons deflected and by how much, we can say where the collision occurred, thus determining the particle's position. However, the authors of such explanations argue that as a result of each collision, the photon and the particle whose position we're determining exchange momentum, meaning that the particle's momentum after the measurement will differ from its momentum before the measurement. Therefore, we lose the ability to know exactly what the momentum was beforehand. This is a clear and intuitive explanation, but it has one major flaw. it's fundamentally incorrect. It gives the impression that the problem lies solely with our measuring instruments and methods. For instance, if we could devise a method to measure an object's position without altering its momentum, and measure its momentum without affecting its position, then logically, we should be able to determine both with precision. But the point is that no matter what methods or precise instruments we use, we can't determine both position and momentum simultaneously with absolute accuracy. Viewing the uncertainty principle as a measurement problem paints this picture: that there exists a particle with all its parameters fundamentally and definitively determined, meaning that somehow within the particle there's complete and accurate information about the values of all the quantities characterizing its state. It's just that we, with our imperfect instruments and methods, cannot fully and accurately extract this information. However, the reality is much more complex and fascinating. The modern interpretation of the uncertainty principle within the so-called Copenhagen interpretation of quantum mechanics states that before the act of measurement, the parameters of a particle are not just not fully and accurately determined, they are not determined at all. The only thing we can say about a particle's parameters before measurement is to describe the probability of obtaining certain values for those parameters as a result of the measurement. I want to emphasize this truly revolutionary concept for our perception of the world. According to the Copenhagen interpretation, the act of measurement does not extract information about a particle's characteristics. In fact, the specific values of its characteristics emerge during the measurement process. According to this concept, before the measurement process, the information about the measured parameter's value didn't exist at all. The act of measurement is like asking the universe a question that it didn't know the answer to beforehand, and each time, the universe makes up an answer according to the instructions built into it, which we call the laws of physics, and then communicates that answer to us. It turns out that among the rules the universe follows when determining an object's parameters is a prohibition on giving precise answers to several questions simultaneously. We are forced to either settle for precisely knowing one characteristic at the expense of losing any chance to learn about others, or accept that we'll get only limited accuracy in the answers to both questions. Here, an important clarification is needed. When we talk about measurement and observer in quantum mechanics, it doesn't necessarily mean an experiment conducted by a human in a laboratory. In fact, measurement in quantum mechanics generally refers to any active interaction between a quantum object and other objects that leaves a trace in the macroscopic world. And the observer doesn't necessarily have to be a person or even a living being. An observer can be anything that somehow retains information about the results of this interaction. For example, a wall illuminated by sunlight is an observer for the photons hitting it. If this concept of a state emerging during measurement seems strange, fantastical, or, to put it bluntly, nonsensical to you, you're not alone. During the early development of quantum mechanics, many great physicists, including Albert Einstein, vehemently refused to accept such an approach. Einstein contested it with arguments like, God does not play dice, and even teased the proponents with analogies like the mouse that creates the moon simply by looking at it. Einstein was a proponent of the measurement interpretation of the uncertainty principle and believed that the information about an object's parameters is inherently present within it, but we just don't yet know how to extract it. This concept became known as the hidden variables theory, and it's worth noting that Einstein's contemporaries didn't find a way to refute it. For many decades, the hidden variables theory loomed like the sword of Damocles over the growing structure of quantum mechanics, until in the mid-1960s, some physicists devised a way to test it, and later, in the late 20th and early 21st centuries, others carried out the tests. I'm referring to Bell's inequalities and the related experiments, which we covered in a separate video. Through these experiments, physicists were able, or almost able, to disprove the hidden variables theory and proved, or almost proved, that the uncertainty principle is fundamental and lies at the very core of the workings of our universe. In quantum mechanics, The uncertainty principle is derived by analyzing the properties of so-called Hermitian operators, mathematical entities used to describe the observable parameters of quantum objects. The proof, by the way, is quite elegant and beautiful, but to fully appreciate it, you need a certain familiarity with linear algebra. Therefore, we will take a different approach, less rigorous and elegant, but more illustrative. Let's start with an even more fundamental principle of quantum mechanics known as wave-particle duality, which states that quantum objects can exhibit particle-like properties in some experiments and wave-like properties in others. We have a detailed video on wave-particle duality on our channel, but for now, here's the main point. The propagation of any quantum object in space represents the propagation of a probability wave, or more precisely, the probability density of finding that object in a particular region of space. The greater the amplitude of this wave at a given point, the higher the probability that we will find the object there when we perform a measurement. Conversely, in points where the wave's amplitude is zero, the probability of finding the object is also zero, meaning that the object simply isn't there. In addition to amplitude, a probability wave, like any wave, has a wavelength, and it turns out that the wavelength of any quantum object, put simply, a particle, is uniquely determined by its momentum according to this classical formula. In other words, if we know the particle's momentum precisely, we also know the wavelength of its corresponding probability wave with precision. In physics, the concept of wavelength is introduced for ideal harmonic waves, which are described by these equations and appear in space as follows. A key feature of harmonic waves is that their amplitude is constant throughout space, meaning they have the same value everywhere. Remember, in our case, this is a probability wave, whose amplitude, or more accurately, the square of its amplitude, is nothing but the probability density of finding a particle in a specific region of space at a given moment in time. Thus, a pure harmonic probability wave represents a situation where we can find the particle with equal probability at any point in space, meaning we cannot say anything definite about its position since it could be anywhere. However, real particles do have a more or less definite position in space. There are regions where we are more likely to find them, regions where the probability is lower, and finally, regions where the probability of finding the particle is zero. This means that harmonic waves are not suitable for describing real particles. Rather, to understand how we can describe the behavior of real particles using harmonic waves within the concept of wave-particle duality, we need to figure out how to transform the ideal harmonic wave, spread out across space, into something more localized. And there is a way to do this. Let's consider a probability wave that represents the sum, or as it's called in quantum mechanics, the superposition, of two waves with slightly different wavelengths, each of which individually would represent the probability wave of particles with slightly different momenta. We get this kind of pattern. The amplitude of the probability wave is no longer constant across space. It now reaches a maximum at one point and gradually decreases as we move away from it. That is, our particle becomes more localized. Somewhere, the probability of finding it increases, while elsewhere, it decreases. Let's make our wave equation even more complex by adding another term with a third wavelength, i.e., adding a third momentum value to the superposition. The shape of the resulting probability wave becomes even more pronounced. The probability of finding the particle where we expect it increases further, and as we move away from that point, the probability decreases even more rapidly. This means that the region where we are most likely to find the particle becomes even smaller. Continuing the process of adding more terms to our wave equation, we get a probability wave that corresponds to an increasingly localized particle in space, meaning its position becomes more precisely defined. However, the price we pay is the increased complexity of the probability wave itself. It no longer consists of just a single wave with a definite wavelength, i.e., it no longer represents a particle with a definite momentum, but rather a sum of waves with different wavelengths, or as we say in quantum mechanics, a superposition of particles with different momenta. When conducting a specific experiment, of course, we will obtain concrete values for both the coordinate and momentum in each case. It's as if the universe chooses one specific wave component for us and discards all the others. The more localized the particle is, meaning the less uncertainty there is in determining its position, the more such harmonic components there will be, and the greater the range of possible outcomes we might observe in a given experiment, leading to greater uncertainty in that measurement. Simply put, for our particle to be localized in space at all, its wave function must be structured so that its momentum cannot be determined precisely. This is one of the rules the universe follows when answering the question we pose about a particle's state through measurement. Again, we're talking about an abstract, theoretically impossible, perfectly precise measurement. But even this would not allow us to simultaneously extract completely accurate information about both position and momentum. Not because this information is somehow cleverly hidden from us, but because there's simply too much of it. The particle itself is constructed in such a way that its parameters are defined within a certain range of values. If we were to apply the mathematical apparatus and formalize all these considerations mathematically, we would inevitably arrive at the conclusion that the relationship between these fundamental measurement uncertainties is described by the uncertainty principle. At this point, my viewers might have a question, or rather, an objection. So, some people came up with something, tinkered with formulas and graphs, and concluded that nature works this way. And now we're supposed to take their word for it. What if they messed up the math, or their graphs don't quite fit? How can we, ordinary mortals, be sure that nature is indeed fundamentally uncertain? How can we get a hands-on feel for the uncertainty principle? And this is an entirely legitimate and valid question. Physics is a highly practical science, and any claim, emphasizing any, only becomes credible after experimental confirmation. However, experimentally confirming the uncertainty principle, especially its fundamental nature, turns out to be quite challenging. The fundamental uncertainties it introduces in determining the values of physical quantities are extremely small. For example, let's say we are studying the properties of a grain of sand, an object with a mass of approximately 10 to the power of minus 9 kilograms, whose position we have determined with a precision of a micron, that is, 1/millionth of a meter. In this case, the fundamental uncertainty in momentum will be around 10 to the power of minus 28 kilograms meters per second, which, considering the object's mass, means a fundamental uncertainty in measuring the velocity on the order of 10 to the minus 19 meters per second. Such an error in measuring velocity is many orders of magnitude smaller than the resolution of even our most precise instruments, and it would be practically impossible for us to detect such an error. The effects related to the uncertainty principle become significant only on subatomic scales, with characteristic distances on the order of 10 to the power of minus 10 meters and characteristic masses on the order of 10 to the power of minus 25 kilograms. And it is challenging for us to conduct highly accurate direct measurements of the parameters of such objects. Nevertheless, we can observe effects related to the uncertainty principle with our own eyes. One experiment where the uncertainty principle manifests itself is the classic school experiment on the diffraction of light through a slit. Let's say we have a light source emitting a parallel beam of light, meaning a stream of photons traveling strictly parallel to each other. Mathematically, this means that if we align the x-axis of our coordinate system with the direction of the beam, the y-axis projection of the velocity, or more precisely, the momentum of all the photons will be zero. Now, let's place a diaphragm between the source and the screen, i.e., a barrier with an adjustable aperture. On the screen, we will see a bright spot, essentially an image of our aperture. But if we make the aperture very small, we will see something strange. A pattern of alternating light and dark bands will appear on the screen. And most surprisingly, the light bands will form even quite far outside the area that represents the aperture's projection onto our screen. In school, this is explained by the wave properties of light. However, let me remind you, we are currently considering light from a quantum mechanical perspective, i.e., as a stream of photons. From this viewpoint, the appearance of light rings outside the aperture's image means that our photons must have somehow moved outside this area, meaning they must have had some non-zero projection of momentum along the y-axis. But before placing the screen in the path of the photons, this momentum was zero. We did nothing to the photons, did not affect their source in any way, yet simply by manipulating the aperture, we somehow caused the zero momentum projection along the y-axis to become non-zero. How is this possible? From the perspective of the uncertainty principle, this result is easily and straightforwardly explained. Indeed, before installing the screen, the position of the photons along the y-axis was not determined in any way, in the sense that we could find a photon with any coordinate along the y-axis. When we installed the screen with the diaphragm, we imposed certain constraints on the coordinates of the photons that could leave a mark on the screen, as only photons with a specific y-coordinate could pass through the aperture. By setting a certain precision in determining the y-coordinate, we simultaneously lost full accuracy in determining the projection of momentum, or velocity, along this axis. After installing the diaphragm, we can no longer fundamentally assert that the vertical velocity projection of the photons is zero. A rule emerged whereby the universe, in answering the question of what specific vertical velocity projection a given photon had, gained some freedom of choice, and photons gained the ability to move outside the aperture's image. Further out, the smaller the aperture. When the aperture size is large compared to the wavelength of light, this probabilistic increase in the vertical momentum projection, driven by the uncertainty principle, is negligible, and we don't see the effect. But as the aperture size decreases, it grows, and the effect becomes more pronounced. One might object, but the results of the diffraction experiment at the aperture are perfectly explained without any uncertainty principle, based solely on the laws of wave optics. Of course, I would agree, but we have been considering light as a stream of particles, photons, rather than as a wave. In this approach, explaining the observed phenomenon without the uncertainty principle would be problematic, and similar phenomena are observed when particles like electrons, protons, or even entire molecules pass through apertures. The point is that these objects also exhibit wave properties, and from this fact, let me remind you, we derived our uncertainty principle, which now, in turn, allows us to reconcile our understanding of quantum objects as particles with experiments that seem to contradict this, such as the diffraction experiment. You can also confirm that the uncertainty principle works by observing effects that arise from and are explained by this principle, such as the tunneling effect, which we have a separate video on, as well as many other phenomena. In fact, if you dig deeper into almost any quantum mechanical phenomenon, at some point, you'll encounter some manifestation of the uncertainty principle. The fundamental nature of the uncertainty principle has already been proven through the ingenious experiments of Aspect, Clauser, and Zeilinger, along with their followers, who tested Bell's inequality, which we mentioned earlier. In our upcoming videos, we will return to the uncertainty principle and its consequences multiple times. And I hope that now we'll be able to discuss this fundamental phenomenon on the same page. Well, that's all for today, dear friends. Take care and see you again on our channel.